activities. And so Vincent DiNoto is going to talk about the satellite positioning and data acquisition. And we'll go ahead and turn it over to him. I guess you have to stop sharing, Mike, so he can put his presentation up.
Okay, give me just a second. Yeah. I'm not seeing my share.
Yeah, we see your screen.
Oh, you are? Okay.
Yeah.
I'm just not seeing a green band around my slides. So you're seeing my slides?
Yes.
Okay, super, super. All right. As noted, I'm Vince DiNoto. I'm actually in southern Indiana, what we call the sunny side of the Ohio River. So I live in Jeffersonville, Indiana, and working from my home office today. And so we're going to talk about geospatial security. And obviously, some of the points that I'm going to talk about are those points that were on the previous slide. As noted, I am the director of the GeoTech Center. My email address is here if you want to get in contact with me. I also work with NCyTE. Your next presentation in April, I'm a co-principal investigator for that grant. So I decided to change my slides yesterday, and I figured I couldn't start this talk without having something about balloons. So this is the balloon that was off of South Carolina. You can see the U.S. military aircraft there. And, you know, what is this? What is the security risk? I don't think anybody knows at this moment. You know, we've also shot down 3 other balloon type objects. So, but it does raise the question about security. How secure are we? How secure is our data? And how can you change that data to let people think they're one place when they're really a different place? So that's some of the stuff that we'll talk about. Sorry. So just a quick slide about what is geospatial technologies, what is GIS, sometimes called geospatial science and technology. It seems like we can't get our name to a single name. It has evolved over the years, but basically anything that we can put on a map is GIS. But if you think of GIS as just something that you can put on a map, then you're really shortchanging the science that's here. So a sense of place, an XYZ coordinate, a temporal location, vector data in raster data. Vector data has a starting point and basically a length and has an angle to it, where raster data is more what we're going to be talking about today, which is really more pictures. So we're talking about raster information. Analysis, just collecting the data, just understanding where it was taken really doesn't do anything for us. It's the analysis. Today, most of that analysis is computerized. A lot of it's moving into the AI field. But it started out being people looking at film. So the analysis has changed. And our science is really driven by software and hardware. You know, massive computing is being done. The software is changing, it seems almost on the hour, but it's actually now changing on the monthly basis, at least the software that most people are using to do geospatial technology. And I intentionally chose the source for this as being the CDC instead of being some geospatial organization, because we think of the CDC with the COVID virus and everything, but a lot of GIS was done during the pandemic. For example, most of you probably at some point went to the Johns Hopkins dashboard to see what was going on. That was an example of using geospatial data. But it was a matter of looking at graphs. It was a matter of looking at charts and some mapping, but it really was much more sophisticated than just looking at a bunch of maps with maybe dots on it showing how many cases there was in a certain area. it was really an analysis tool that could be done on the fly. So some of the things I'm going to talk about today is I'm going to talk about what is GPS/GNSS, because we really use this term wrong. And so we'll talk about a little bit about GPS and GNSS and how you can hijack this. So what is coming down to us on the data pipeline, and how can you hijack this data? We're going to talk about remotely sensed data. A lot of our data that we get is not data that is us going out and measuring it directly, but it's coming from aircrafts, drones, potentially satellites. So we're going to talk about remotely sensed data. And then we're going to talk about open sourced maps. And in some ways, we're going to be talking about ethics as part of that, because what is ethical to share, for example, when you're in a war? So as we look at what's going on with the Ukraine and Russia right now, and we look at the open source mapping that's there, what is appropriate and what's inappropriate that we should be sharing? There's not a right answer, there's not a wrong answer to that, but it's something that we should think about. So let me start with talking about global positioning satellites. And it looks like I have a typo there. I left off the G in GPS. When we talk about GPS, we talk about this as the constellation of satellites that's around the Earth, but that's really not the correct term to be using. We should be using GNSS, Global Navigation Satellite Systems, because the GPS satellites are only those of the United States. And if you look here on this slide, you can see all the different other constellations that are out there. China's got their constellation, Galileo's the European constellation, Russia's got theirs, India, Japan, and to some degree, the UK, Australia, the Republic of Korea, so on and so forth. They all have their own global positioning satellites out there. And the GPS satellites really are the 24 that represent the United States. As this diagram shows here, and I'm not sure why it's not automated right now, but it shows these satellites are constantly orbiting the Earth. And when I use my phone, I pick up my phone and I look at my position, I may be connecting to 2 Russian satellites, 5 US satellites. It's hard to say, but their signals are open in general. They're not masked that you can't use them, but in general, most of these signals are all open. The United States right now is in the process of upgrading its satellites, putting new satellites in, taking old satellites out of service. And so over the next several years, you'll see that this is changing. Whoops. So as I said, there's 24 satellites that orbit the Earth. If a satellite dies, we do have a couple spares out in space that we can replace it with and reposition how that satellite's orbiting. But in general, the GPS is 24 satellites, the US satellites. So what are we getting when I pick up my phone and I look that I'm connected? When I look at my location on my phone, what is my phone receiving? My phone is receiving a timestamp. So if I know the time it took for that signal to get from the satellite to where I'm at, and by knowing that time, I can know a distance. But that's one distance. So we've got a single satellite sitting out here in space, and we know the distance from that satellite to my position on the Earth. But it's not just my position, it's a sphere, because we have one radius and we have a sphere that is at radial distance. Now, only part of that radius intersects the Earth. So a single satellite doesn't give me anything. If I take a second satellite that I know its precise position in space, and I know its timestamp, I know its distance away from me, and now I can start doing some triangularization. I'm somewhere along a line. If I bring another satellite in, I can get to, I'm somewhere on this plane, a single point on this plane, but I don't know exactly where I'm at elevation wise. And I bring a 4th satellite into my calculations, and now I can start to develop a 3-dimensional model. So once I develop that model, the more satellites I bring, the more precise my location becomes, but it's all based upon time. It is all monodirectional. I'm only receiving information. I'm not sending any information back to that satellite. So that's a misunderstanding that a lot of people have. They assume that you're communicating back in space. So for example, if you're in a large truck, what that large truck is doing, it's receiving its position because it has a GPS antenna, but it then also usually connected to some type of satellite cell phone or a satellite phone, and it's sending that back to the company what its position is. So it's constantly communicating with the company. I'm a bike rider, and so one of the things I can do when I go out for a ride is I can let my wife know by an app that I'm going out for a ride, and she can actually monitor my position. So my phone is receiving these timestamps from the GPS satellites. It knows my position as I'm riding. It's using the cellular capacity of my phone then to send an information back to my wife's phone, and that she can watch where I'm actually riding. And so actually the way I have my bike set up is if I'm stopped for more than 3 minutes, it sends an alert to my wife saying that I'm stopped, that maybe something's wrong, and I get a phone call in general. So you can see how that type of situation works. We can also have ground-based stations. So if you're trying to land an instrument landing of an airplane at an airport, you're probably connecting to what's known as a wide area augmentation system, the WAAS. And that system then gives you ground-based information along with the cellular information to give you a more precise location of where you're at. If you're into agriculture, one of the things that you might do is you might put a base station on the corner of a field, and you might have a combine that is self-driving, and that combine then takes and drives the down the field, but to know its position more accurately than what you can get just using the GPS, for example. We put ground-based stations that we precisely know where they are at. And then I mentioned a couple others. Accuracy today can approach 1 centimeter. That's pretty accurate, 1 centimeter. Again, it depends on the number of satellites, depends on the ground stations you might be connecting to. There's a lot of things that it depends upon. And when the GPS satellites were first put in space, we blocked the last digit. We, the federal government, blocked the last digit coming there on the timestamp. So we couldn't get as many decimal places, if you would, for our accuracy. Therefore, the original GPS units did not see as accurate a signal as we see today. And therefore, what happened was, excuse me, what happened there was that we were maybe within a few feet of where we were. We weren't within a centimeter or 10 centimeters or so of where we actually was positioned. Back in 2000, the US quit blocking that last digit, and now we have a much more accurate position that can be used by surveyors and other people such like that. So the security, we all have, well, not maybe not everybody, but we have phones. They're receiving this information. We got these precise positions. We know we're talking about self-driving cars. We need to have accurate maps for that. We need to have good GPS information for that. But what happens from a security standpoint? What can you do to that signal so that I don't know where I really am? So one of the things you can do is you can jam the GNSS or GPS, if we're talking about just the United States constellation. You can basically, by knowing the wavelength that's coming from space to your device, if somebody puts a very intense source that's broadcasting that wavelength, all of a sudden you can jam the signal that's the true signal because you got this other signal that is basically garbage, and therefore it doesn't receive the signal from the satellites. So you can jam the GNSS system. You can also do what denial of service. Denial of service can be that you write a new signal that's going out, and that new signal that's being received tells it you can't connect to the satellite. It gives bad information basically, and therefore again it's blocking what's coming from space, and we get this denial. Or you can do what was done in the Black Sea area, and I'll talk about that in a little bit more detail in just a moment. You can come in here and you can tell it, oh, here's my timestamp, and by giving it enough different timestamps, the person using the GNSS system thinks they're somewhere else. So if you think about today's weaponry, a lot of it is GPS driven. Well, if we can tell the weapon it's in a different place than where it truly is, therefore you can change where that weapon is targeting. So one of the concerns is, how do you fix that? And a company called Here is working on that, and this is one of their slides. Basically, don't use just the GPS or the GNSS, but also use Wi-Fi and cellular and networks that all have to have positions associated with them. And by getting signals from all these different positions, you can then be much more accurate. This started was because when you're in a downtown with tall buildings, the buildings tend to block a lot of the GNSS signals. So you have this canyon effect. And so why this research was started was, well, if I'm driving down a city street and I've got tall buildings around me, I might not know where I'm at because I'm blocking quite a few satellites. I can only see those that are directly overhead. And therefore, by creating another system, like using cell phone towers and things, you can help guide where you're truly located and things like that. So you're going to see a lot more of this type of technology, both from the jamming of signals, but also as we look at driving. You know, if you have a self-driving vehicle, you don't want it not to know where you're at when you're going down a city street. So this is coming. So is this real? Yes, during the beginnings of the Ukraine-Russian war, there was a lot of jamming going on, and by this jamming, it was giving false position. But not only did it give false position in the Ukraine, but the Black Sea area, Eastern Finland. Okay, let me continue. The Baltic area, the Mediterranean, Cyprus, Turkey, Lebanon, Syria, and Israel, as well as northern Iraq, all was having problems with being jammed. So that's a large percentage of the country. By jamming it, then you can no longer use your GNSS system, which doesn't just affect where ground troops are, but it affects aircraft, it affects weaponry on how they are being targeted. So this happened about exactly a year ago. So let me stop there and see what kind of questions you might have, or if we have any questions right now before we go into the next topic.
You can put your questions in the chat or just unmute yourself and ask the question.
Okay. Not hearing any at this moment, I will continue. So the next topical area I want to talk a little bit about is the topic of remote sensing, of how data has changed, and to give you a little bit of a historical perspective on this. So some of our first imagery that was taken by either hot air balloons or taken by kites. So they had cameras on the kites, and you can see a little piece of a image here that was taken by a kite. But you can see that was one way of obviously getting up above the ground to get a bigger perspective. If you are a Civil War historian, you know that the Union Army had balloons that they used to also look, even though they didn't very effectively use them, but they also used them to look at enemy positions. This is a true picture. The next area that we used was using pigeons. They would actually strap cameras on pigeons. They would set a timing circuit on the camera. So every so many minutes, or maybe it was in seconds, it would take a picture, and eventually the pigeon would return home. They would take the camera off the pigeon, and they would develop the film. And this was aerial reconnaissance work. And you can see some of the type of pictures that were obtained by pigeons. So pigeons were our first animals, at least, used to do remote sensing. Then in the late 50s, early 60s, we placed spy planes. U-2 was the model of the plane that was used at high elevations, flying at 70,000 feet or higher. And this is a picture of a U-2 plane. At some points in time, the U-2 planes were controlled by the CIA. Later, they became instruments of the United States Air Force. And other countries were doing some similar things, but not probably as high as what the US planes were flying. A couple of these planes were shot down, one over the Soviet Union and one over Cuba. So then comes October of 1962. I'm not sure how many of you are old enough to remember this. I just vaguely remember what was going on in 1962. But this image here shows some of the first detection of missiles in Cuba. So we're now using remote sense data for geointelligence. I've given you a few links here that you can read more about this, but it was decided that the imagery we had from the U-2 spy planes were not good enough to share with the American public. So President Kennedy ordered the Navy and the Air Force to fly jet fighters that had been equipped with a bunch of cameras at 1,000 feet over Cuba at 500 miles per hour. And as I was researching some of this for this presentation, it surprised me that there is film that really has never been looked at that was flown. There was lots of sorties flown over Cuba during October of '62. And some of that film has really never been looked at. That film is all in the National Archives. And since it's been enough years, those items are now released to the public, but they don't publish a list of numbers. You have to sort of know their numbering system to be able to figure out where that film is in the National Archives. It's in a cold storage, I believe in Kansas, if I remember correctly. Another thought that was developed was if we could put satellites up in space and had these satellites taking pictures of troubled areas, or puts a satellite in a geosynchronous orbit potentially, but have the satellites taking pictures. Well, at that time, satellite technology wasn't to the, or I should say optic technology wasn't to the point that we could be doing what we do today with satellites. And that being that we have solid state chips on the satellite, and it receives the information and it transmits that information back to the Earth. Instead, we were still doing film type imagery with satellites. And so I'm going to show you a piece of a video. This is kind of a neat little video.
as they exist today do not.
Once President Eisenhower made the decision to take photos from satellites, the NRO then faced the technical challenge of getting those images safely back to Earth, where they could be analyzed by awaiting photo interpreters. An ingenious and rather simple solution emerged. Drop the undeveloped film in a bucket and have an airplane snag it in midair before it's splashed into the sea.
You're looking at an object that's going about 200 feet a second.
This is the story of the bucket catchers and their historic last KH-8 Gambit catch in April 1986.
I mean, I felt so much pressure. Don't mess up. This was your chance.
Okay, we'll stop it there because it goes for about 5.5 minutes. So you're welcome to take a look at that if you'd like. It's up on YouTube. And so we dropped buckets containing undeveloped film and basically C-135 aircraft, I'm sorry, C-130 aircraft, I believe it was, hooked onto the parachute, reeled it back into the airplane. And we did this till 1986, even though we had started developing solid state optical detection devices that had reasonable resolution, but they still didn't have the resolution that we had on film. And for this type of work, we needed that resolution. So at this time, we're flying high flying aircraft and we have satellites in orbit. Is how we're getting data about what's going on in the world. So I want to take you through a little bit of an exercise here on the amount of data that we capture and the resolution of the data. So the resolution I'm also going to show you in some imagery in just a moment. But if we use a Landsat satellite, and we still have Landsat satellites, and we use them a lot for agriculture and other purposes, each of their pixels is 30 meters on a side. So a single pixel element represents 900 square meters. Basically, about 4 pixels would encompass an entire football field. Well, then comes along the Sentinel satellites, which are still orbiting. Their image size is about 10 meters. So each pixel has a much better resolution, about 9 times better, because we're looking at 100 square meters. And basically a football field now takes 44 pixels to cover it. You're starting to get a little bit better resolution. Digital Globe, another satellite system, we're looking at about a foot resolution, or we got 9,375 pixels representing the same area as what we, yeah, that's right, representing the area of the single Landsat image, and about 7,000 pixels now represent a football field. We go to aircraft. Aircraft is anywhere today between 2 inches and about 6 inches, depending on the elevation the aircraft's flying at. And we're talking about, in general, low flying aircraft, we're talking about 15 centimeters, or about 40,000 pixels to represent that football field. And if we go to uncrewed aircraft, now we're talking about a half an inch. And we're looking at 6 million plus pixels to represent that football field. Or I'm sorry, to represent the same size area as one single Landsat pixel. We also now can steer satellites or aircraft, and we can set pathways. We also can vary the color depth. So initially we had 8-bit color. Usually the way it's done, it was 3 sensors to get 8-bit color. And we can then move to 10 sensors, and some things are now up to 16-bit resolution. We still have problems with weather. That problems with weather can be both for ground-based aircraft and UASs, but also with satellites. If there's a cloud passing under that satellite, we get no data. And we can have multiple sensors both in the visible range, the near infrared range, which is great for agriculture and plant use, and the thermal infrared range. But as we think about security of information, who can see this information? So let me first show you a visual of this, and then let's talk a little bit about the information. So here's a Landsat image. You cannot make much out from this single Landsat image. If you were looking at a big field of crops, yeah, you could determine some things about this field. But if you found an area, let's say, that had disease in it, like where my mouse is moving, you might have to remove 30 meters by 30 meter area. That's the smallest you'd remove. So you're probably going to remove at least 10 times that area. That's a big part of a field that you might have to remove the information or remove the crop from. Sentinel, same location on the Earth. Sentinel, much better resolution. Digital globe, you can now start to make out the individual buildings. This is, by the way, my campus. My office sits right there. We go to aircraft. This is 3-inch data. So you can start to see even higher resolution. And if we go to an uncrewed aerial vehicle, you can get even much more precise. You can almost get down to the individual leaves on the tree. So as we get this better resolution, we get this better information, it really changes the intelligence community. So here I've got 2 images of a bridge in the Ukraine.
I see.
And this information was taken by Maxar. So what this is a bridge that's right in this general area here. This is a Google image. Notice it shows that the bridge is blocked or slow traffic. But you can no longer say, no, this didn't happen, because today open source satellites are taking imagery in real time and showing us what the true effects are. The angles are actually reversed on, let me make sure I'm saying that right. Yes. The picture, these 2 pictures are 180 degrees out of phase with one another. So it was just this is just raw imagery that I found from a speaker that I used on a presentation for my center. And you can see, okay, now I'm showing real time. Now we need to think a little bit about that ethics question. Is this something that we should be publishing? We can debate that one way or the other, but you can see the type of data that can be collected in real time. And let me move then to this ethics question a little bit more. This is OpenStreetMap. I'm not sure if you're familiar with OpenStreetMap. OpenStreetMap is an open source mapping program. It creates citizen scientists collecting information, mapping that information, and this is a vectorized mapping done, and then to make it run faster, the vectors are made into rasters so that you actually have an image that you're looking at here instead of just a bunch of vector information. This is updated in real time. And if you look real careful, and I don't know if you can notice it on your screen, but like over in this area right here, you can see these lines. What are those lines? Those are power transmission lines. This is open source. I gathered this information a week ago, maybe 10 days ago. I'm in the Ukraine, I'm north of Kiev, and I am seeing transmission lines. You can see every individual building. Who plotted all this information? It was plotted by individuals. It's not taken from other data sources. This is basically plotted by a group of individuals. Who can plot it? Anybody that wants to sign on can plot it. Is there misinformation plotted here? Potentially. But again, it raises that question, should we blur areas or should we keep them at full resolution? And as you look at this area, if you weren't aware, the area I'm looking at, this is Chernobyl, where the power plant accident occurred years ago. And finally, if we move down to here, this is what Google Earth of the same region does. They don't show the individual buildings basically on the same type of a zoom level, but they do show where the power plant was and things like that. But they show a little bit less detail. They show still major roads though. So those are all shown. They show water features very accurately. And so Google Map can have individuals helping with the data sources and things like that, but it's not completely open source like OSM is completely open source. So let me stop at that point, show you a couple things here. My email address, feel free to contact me. My center's URL. We're putting a program on in April called Earth Observation Day. You can register by following that link or find out more about that program. We're also doing a bunch of professional development events, and you can find out more by doing that hyperlink. And finally, we're putting together a teacher certification program, which will start in May. And again, you can find out more at the professional development link. So I'll stop at that point and try to answer any questions that you might have.
Again, you can put your questions in chat or unmute and ask the question. Vincent, I had one question around just when you're talking about the security from the satellite perspective. Do they have a way to monitor the satellites and the data to see if there's any disruption from some kind of a central control system?
Well, that's one of the issues because, all right, if we're talking about the GNSS satellites, they're just sending out timestamp, constantly sending out timestamp, and then other devices are determining that. So it's the local device that gets jammed. It's not the satellite. That data is still coming from the satellite. We're not jamming the satellite. We're jamming the receiver. And so therefore, sometimes unless a military or an operation that's looking at high resolution imagery, or not imagery, but data for positions, starts finding issues, it's not knowing that it's being jammed unless that signal's, the jamming signal's picked up by someone who does something about it. You know, it could be nothing more if I'm using my cell phone and using my position location, and all of a sudden it looks like I'm 3 blocks away from my house and I'm not really on the right street. You know, we tend to say, I wonder what's going on there. We don't think about it, but I could very well have been jammed. The Somali pirates, back several years ago when they were taking ships and things, they made the ship think it was in one place when it was in a different place. So therefore, when they sent out SOSs, some of it was sending people to the wrong location, not where the ship truly was.
Okay, so that sounds logical. You were talking about ships. If you can buy these EPRs that help locate you, how do they do that? They tie that off of a satellite image to. I know I've helped my son sail his sailboat from Mobile, Alabama to New York City, and we had EPRs on board, which is supposed to be if we had serious problems, we could activate the EPR and the Coast Guard could be called out. Is that the same principle?
Right. It's basically the same principle as what we're talking about, like with trucks and things like that. It's determining your position by using GNSS satellites. And then if something happens with whatever parameters they put in there, something happens like you don't communicate with somebody, let's say for 6 hours or whatever, then it automatically sends a call to the Coast Guard or with your last position, known position and things like that. So it's sort of the same thing I was talking about when I go bike riding, that I can have signals sent to my wife when I'm not moving.
Okay. So anyone else have any questions? It's new to this group, I think, as far as from a securities perspective. Let's see, I think we had something. Okay. Well, if there's no other questions,
Stephen, not necessarily a question, but this is the same type of technology Apple's building into their Apple Watch Series 8 for hikers. If they get in trouble, they can ping a satellite to get help to them.
Exactly. I think they're using some type of a satellite cell phone in the watch to do that, because obviously if you were just doing cellular towers and you're out in the middle of nowhere, that's not going to be much good for you. So I think it's communicating via satellite cell phone and not traditional cell phone technology.
It is hitting a satellite because they got, some procedures. It's still fairly new because they just rolled it out in their recent phones, and they have a ruggedized watch that hikers will wear, and that helps them.
Yeah, and let me just make sure I reemphasize, because I've seen this misprint in many places. The GNSS satellites themselves are monodirectional. They're only sending data to the receiver. The receiver doesn't communicate with that satellite, so the watch or the cell phone is actually communicating with, a different satellite.
okay. One other thing I was thinking about, we have different standards for security, like NIST standard 800s series or something like that. Is there something like that they have for satellite security and best practices?
Not that I've seen, but I'm not a person that I don't have enough knowledge to know for sure if there is anything there, but nothing that I've came across in my research and things.
Okay. Okay, anyone else have any questions? Well, Vincent, thank you. That was very interesting. I think something to think about, and another area of security that we need to think about. And so I'm going to turn this back over to Mike for any final comments.
Thank you, Stephen. Well, my final comment is thank you for attending today's member meeting. We have more member meetings coming up, and we like to see you attend those as well. If you do have some feedback, I dropped a link in the chat. Please click on that and send us your information about events that you want to see coming up. Maybe you're interested in presenting on a topic. We'd love to get your feedback on that. With that, I don't have anything else to add to the meeting. Thank you, Vincent, again for presenting. It was very satellites and geospatial technology and the implications of that with everything that are going on. So thank you, everybody. I won't keep you any longer. I'll give you back some of your time. Have a great weekend.
Thank you.
Thank
Bye,
you.
everyone.